Okay, now in this example, we are asked to, what is the fifth root of 16 times the fifth root of 8 in reduced radical form. When you multiply radicals, the first thing you want to check is that the index is the same. If the index is not the same, then it becomes a little bit complicated of a process, but for the most part for Algebra 2, index will probably be the same. After checking that, the way you multiply radicals is you multiply their coefficients. In this case, neither of these radicals have coefficients, or their coefficients is 1, depending on how you want to view it. Since there's nothing outside originally, there's not going to be anything outside after we multiply. And then after multiplying the coefficients, you want to multiply the radicand, or the stuff underneath the radical, as what radicand means. So 8 times 16 is 128. Anytime you multiply radicals, though, you want to make sure you simplify the radical as far as possible. Sometimes you can simplify it beforehand. I usually just wait until afterwards to try to simplify the radical. Now, as far as fifth roots go, I don't see 128 on my chart. 128 would be right here if it is a perfect fifth power, but we don't see it there. So we need to check to see if there's any fifth powers that go into 128. The only one we really have to check is 32, because 1 won't really get us anywhere. I believe 32 goes into it evenly. Yep, so we'll separate it into the fifth root of 32, and 128 is 32 times 4. If we break that apart, it's the fifth root of 32 times the fifth root of 4. And the fifth root of 32 is just 2, but we can't simplify the fifth root of 4. So there we have it. Now, in this example, we are asked what is the sum, or I guess difference in some cases, of this expression. So as we look at this expression, it's connected by addition and subtraction. And the way you add and subtract radicals is, first of all, they have to have the same radical in it, meaning both the index and the radicand has to be the same thing. And then once they are the same thing, you just add the coefficients just like you do for like terms, like 2x plus 3x is 5x. And adding and subtracting radicals is a very similar fashion. But first, we have to break down the radicals to see which ones are like terms. So, for the square root of 20, well, 20 itself, it's not a perfect square, but I do know 4, which is a perfect square, goes into 20, and it's 4 times 5. I'm going to skip a little bit of steps here as I go through it. The square root of 4 is 2, so we have 2 square roots of 5. The second radical is a cube root of 16, and I know 16 is not a perfect cube, so I need to separate it. Perfect cube that goes into 16 is 8. It's 8 times 2. So the second radical is going to become cube root of 8 is 2, so 2 cube roots of 2. For the next one, 250. 250, yes, 250 is not a perfect cube. However, I do know there is a perfect cube of 125 that goes into 250. It's 125 times 2. The cube root of 125 is 5. So 5 cube roots of 2. And then the last one is just square root of 5. Well, 5 is not a perfect square, and there's no perfect square besides 1, which is not helpful here, that goes into 5. So we can't really simplify that last radical. So first, when you're adding and subtracting radicals, you want to simplify all the radicals. Next, you want to combine like terms. So the first term has a radical 5 in it. Do we have any other square roots of 5? We have one right here. So we're going to add or subtract the coefficients. In this case, it's 2 minus 1. 2 minus 1 is 1. And the radical doesn't actually change when you add and subtract. Next, I see a cube root of 2. Any other cube roots of 2? Well, yes, we have a cube root of 2 here. It is negative 2 cube roots of 2 plus 5 cube roots of 2, which is positive 3 cube roots of 2. So overall, this is the answer. You may also see it written without the 1 because the 1 is implied as a coefficient. And there you have it. Okay, in this example, we're supposed to simplify this expression. Now, it may look crazy and new, but if you've been doing algebra, then you probably know how to do this. And the way we start this problem here is the same way you start multiplying x plus 3 times x minus 2. It's just distribution. Now, it does involve radicals, but it does start off as distribution. So going through, 3 times 2, well, 3 times 2 is 6. And then 3 times 2 radical 3. Now remember, when you multiply radicals, you multiply the outsides together, the coefficients together, then you multiply the numbers underneath the radical together. Since the 3 doesn't have a radical, the radical 3 is just going to come along for the ride, but we will multiply the 3 times 2, giving us positive 6 radical 3. Then we're going to go through with our next term, our negative 4 radical 3. Negative 4 radical 3 times 2 is going to be negative 8 radical 3, multiplying numbers outside the radicals together. And in this case, since we don't have stuff inside both, we'll leave the radical 3 as radical 3. And then negative 4 radical 3 times 2 radical 3, multiply the numbers outside together. So negative 4 times 2 is negative 8 radical 3, not radical 3 this time, because they both have radicals. We actually have to multiply the stuff underneath the radicals as well. So radical 3 times radical 3 gives us a radical 9. Very similar to when we do x times x squared the exponent has to change. Well, when you multiply radicals, the stuff underneath has to change. After doing that, it's now an addition and subtraction problem, so we want to simplify any radicals that we can. The square root of 3 cannot be simplified. Again, square root of 3 cannot be simplified. But the square root of 9, well, the square root of 9 is 3. It's a perfect square. So that last term is really negative 8 times 3. In other words, negative 24. Then we just combine like terms to finish it off. 6 minus 24 is negative 18. And then 6 radical 3 and negative 8 radical 3 means we're going to do 6 minus 8, which is negative 2. When you add and subtract, the radical does not change. Just like when you add and subtract with variables, the variable doesn't change. And there we have it. Okay, this is something a little extra. I said earlier that when you're multiplying radicals, you want to make sure the indexes are the same for the radicals. But can you multiply it if the indexes are not the same? Well, the answer to that is yes, but it's a little bit more complicated. You do need to have the same index to actually multiply them. Currently, the first index is 3, the second one is 2. So, if I change this into a fractional exponent and work with it in that form, it would be easy to actually figure out what's going on and how I could actually multiply these. So going through, changing it into a fractional exponent would turn this into 4. Since 4 doesn't have an exponent, it would be 1 over 3 times, for the other one, it would be, again, the 2 doesn't have an exponent, so it would be 2 to the power of 1 over 2. Now, I want the indexes to be the same. The indexes are the bottom numbers on these fractions. So that's what I'm going to focus on. Could I change it in a way of finding a common denominator to make those bottoms the same? Well, yes. The common multiple between 2 and 3 is 6. So I want both bottoms to be 6. Meaning for the first fraction, I'm going to have to multiply the top and bottom by 2. And the second fraction, I'm going to have to multiply it by 3. Which gives me 4 to the power of 2 over 6 times 2 to the power of 3 over 6. Now there's a number of ways I can approach this from here. I think I'm going to look at it in terms of the radical form, just because I'm really emphasizing the fact that you can actually multiply these radicals. So I'm going to go ahead and turn it back into the radical form, which is not actually necessary. I'm just doing it to emphasize this point. There are other approaches. So if I turn it back into the radical form, this is now the 6th root of 4 squared times the 6th root of 2 to the 3rd. If I simplify the exponents, so we have the 6th root of 4 squared is 16 times the 6th root of 2 to the 3rd, which is 8. Then we multiply those. Since they do have the same index now, we can actually multiply the numbers underneath. Is the 6th root of whatever 16 times 8 is. 16 times 8 is 128. Oh yeah, we did that one earlier, I believe. And I believe 2 to the power of 6. So 128 is not a perfect 6th power, but there is a 6th power that goes into it evenly, and that is 64. 64 is the 6th power of 2. 64 times 2 is 128. And then the 6th root of 64 is 2. 6 roots of 2. So overall, that's what it would become. And of course, there's other ways of doing it. For example, I could have rewritten this back here. Oops. Not sure what's going on there. There we go. I could have rewritten it back here as, since they have a common base, I can pull that out, writing it as 4 squared to the 1/6 times 2 to the 3rd to the 1/6. Same exponent, so we can use exponent properties to pull that exponent out farther, making it 4 squared times 2 to the 3rd, raised to the 1/6 power. And then, of course, simplify that farther, giving us 128 to the 1/6, which we would have had to turn it back into the radical and broken down the radical from there. So there's a number of approaches that you can take with this, but the point is you can actually multiply radicals if they don't have the same index. It just becomes a lot more complicated.